This lecture covers section 6.4. At the end of today's lecture, you should be able to understand and apply the allowable stress design model to properly sized components. When we design something, we select materials and component sizes to prevent failure, which is the state or condition in which a member or structure can no longer function as it was intended to. There are several modes of failure, all of which depend upon characteristics such as material, loading, rate of loading, environmental conditions such as being near salt water or changes in temperature, etc. There are three primary failure modes we'll discuss in this course. The first is elastic failure, which occurs when the elastic limit of a material is exceeded and excessive, unrecoverable elastic deformation occurs. This is the failure mode we'll be designing around. The second is yielding, or slip failure, which occurs due to excessive plastic deformation. On the stress-strain curve, we can see that during this type of failure, the strength of the material is reduced because there is less force required to continue to cause deformation. Fracturing occurs when the ultimate yield point is reached and the material ruptures. There are significant material properties associated with each mode of failure. If we're interested in the elastic failure of a component, we would want to focus on the elastic modulus, E. If we're interested in yielding or slip failure, we'll look at the yield strength, sigma y. Lastly, if we're interested in the material fracturing, we'll look at the ultimate strength, sigma u. Once we've identified the mode of failure and the corresponding significant material property, we can construct a mathematical model. There are two ways of doing this mathematical modeling. One is probabilistic modeling, and the other is the allowable stress design model, which will be the focus of this lecture. Under the allowable stress design model, the design is satisfactory if and only if the strength of the component is greater than the stress developed within. The allowable stress design model introduces a concept called the factor of safety. In reality, the loading of a component we design may differ from what we anticipate, and there are other factors that are hard to take into account. The factor of safety serves to account for what we can't. In using a factor of safety, the allowable stress design model dictates that the strength of a component must be greater than or equal to the factor of safety times the stress developed within the component. The value of the factor of safety should always be greater than unity. For example, let's consider an axially loaded rod where the mode of failure is yielding. We want to determine the minimum diameter of the rod per arbitrary loading, material properties, and factor of safety. Since the mode of failure is yielding, the significant material property is yield strength, sigma y. So, within the allowable stress design model, the left-hand side is going to be sigma y, which must be greater than or equal to the factor of safety times the stress developed within the model. We'll insert the equation for stress, R per A, into the equation to get sigma y greater than or equal to the factor of safety times R per A, where R is the internal reactionary force and A is the cross-sectional area of the member. We'll then insert the equation for the area of a circle to get sigma y greater than or equal to the factor of safety times 4R per pi d squared. After solving for the diameter, we're left with the minimum diameter must be greater than or equal to the square root of 4 times the factor of safety times the internal reactionary force per pi times the yield strength of the material. Note that as we increase the factor of safety, there will be a nonlinear increase in the minimum diameter. Additionally, as we select a material with a higher yield strength, there will be a nonlinear decrease in the minimum diameter.